Right, good morning. What I want to look at is engineering mathematics in regards to the periodic function and periods. Excuse me. Now this refers to the periodic cycle of a sinusoidal AC waveform. Okay. Now amplitude is the name given to the maximum or peak value of a sine wave. Each of the graphs shown in figures 23.13 to 23.16 has an amplitude of +1, i.e. they oscillate between +1 and -1. However, if y equals 4 sine A, now you should have enough mathematical skills already to begin to look into this. Okay, y is the value which would be on your graph equals 4 sine. Basically, you're saying here 4 times sine of A. Now, A is going to represent your angle at which the cycle will meet along the horizontal axis, okay, of your waveform. Right, so each of the values in the table is multiplied by 4, and the maximum value and thus amplitude is 4. Similarly, if y equals 5 cos 2a, the amplitude is 5. Now here, when we said the amplitude is 5, we mean it'll be 5 amps or 5 volts, depending as to whether you're drawing the current waveform or the voltage waveform, okay? Okay, and that's 360 over divided by 2. Now obviously we use 360 because it is a complete cycle, okay? And a circle is 360 degrees, same as a sinusoidal waveform would be 360 degrees through its complete cycle. Okay. Now all I've done here, now do the examples. Now you will have some mathematics books and they will give you examples to work. You look at the Let's Go Principles books, use those as your guide. Now for me, you need to make sure that you can understand the concept of y equals whatever the values is. Now in some cases here you can also draw out a table. X would be at a given value, and then you will have X times whatever, basically, or whatever, etc., etc. Now here, just making sure that I've got everything in view, okay? Just checking, making sure. Right. Now, all this I've said here is problem 4. Sketch y equals sine 3a between a equals 0 and a equals 360 degrees. Now here, because it simply says y, sketch y equals, the value will be 1. So your amplitude is going to be 1. So here your amplitude will simply be 1, but it has not given you that y equals 7 or 3 or 4 or anything of the sort. Okay, so here y equals sine, but you don't need to put 1 here. Sorry about that. Now, so here we have 1 and period equals 360 over 3. Now, where did we get the 3 from? The 3 came from here, okay? Make sure you can see the 3. Sine 3a, okay? A represents the angle in each instance of time in respect of your waveform. Okay? So 360 divided by 3 equals 120. Okay? Just checking that I'm in view. Okay? Now equals 120 degrees A. Sketch of y equals sine 3A is shown in figure 23.17. Okay, and here we have sketch y equals 3 sine 2A from A equals 0 to A equals 2 pi radians. Now, you need to know what pi represents as an angle in regards to degrees. Okay, and I can tell you it should represent 180 degrees. So if you're taking 2 pi, then that's 2 times pi is 360. Okay, but I don't need to tell you that. Find that out for yourselves. Make sure that the information I'm providing corresponds to what you have read and seen and have been shown in your classroom. Okay. Amplitude is free. Again, here we have the amplitude is free. So we have a 3 here, and that tells us ties in with this here. Okay. Now, all I'm doing here is taking the time to go through a criteria with you. Okay. Remember that pi rads or equal 180. Okay. Now you need to be sure you understand this concept here for yourself. Okay. Right. So you can see what it means and what it is referring to, and how you get 360 in regards to pi. Okay. And here you have your waveform. Okay. Now, just as a question for you as well, in regards to the, sorry about that, in regards to figure 23.17, and if we go back up, see here that we have an angle of 120 degrees, okay? And you can see here that we have here y equals sine 3a, and that's our graph. Now remember, you would plot this graph based upon the information you have been given in regards to the y equals sine 3a, okay? And you'll need to write out a table giving the relevant values for y at a given value, basically, okay? So starting from 0, you can see here we are going through our waveform, okay, basically. Now, just as a question, what's this point here? What degrees would this point be here? Okay, and that's all. I'm just acting as a devil advocate. What degrees would this? What that would be that point? Degrees of that point there where it contacts. Okay. And here we have the figure for 23.18, and here 23.18 is saying y equals 3 sine 2a. Okay, now let's just go back up a little bit. Okay, make sure that you can see the one that we're talking about, 23.18, and equals problem 5, sketch y equals 3 sine 2a from a equals 0 to a equals 2 pi radians. Okay, and that's what we're looking at. 23.17, and we have 23.18. Okay. Now, again, what's the difference between this waveform and this waveform? What's the difference? Okay, all right, let me just see if I can just bring them in a little bit. Okay, now there's a slight difference. I'm not going to say anything further on that, but I'll leave that for you to think about and to look into for yourselves. Okay, can't be telling you everything, because I know some of you guys out there is quite smart. Okay, what I want to look at now is problem 6. Sketch y equals 4 cos 2x from x equals from x equals 0 to x equals 360 degrees. Now normally I would do a table for this for myself, not normally, okay? But in this case here, you can see here that we have sketched it out here, okay? And this is being done on your behalf. So you have an example how to show how this should be done. And remember, this here would be, it's starting there, so in my view here, this would be lagging basically. Okay. But I could be wrong, so again, check and confirm that for yourselves. Okay. I'm not perfect as I am handsome. Okay. Just remember that, please. Thank you. Now, problem 7. Sketch y equals 2 sine 3/5a over 1 cycle. Now here we've taken amplitude equals 2, comes from here. Period equals 360, because we know the cycle has to be 360, divided by 3/5, okay? Now, all we've done here is multiply the top by 5 and the bottom by 5. And if we can multiply the top and the bottom by 5, 5 at the bottom will cancel out, okay? And that will leave us 360 times 5 divided by 3, which equals 600. Okay. Now a sketch of y equals 2 sine 3/5 a is shown in figure 23.20. Okay. Now make sure that you've done this calculation for yourself so you understand how we got to 600. Don't just look at it on the screen. This is not your work, this is my work, okay? And here we have a full sinusoidal waveform, okay? Now, with problem 7, you will see they have multiplied both top and bottom by 5. Having multiplied the bottom by 5, it will simply cancel out, leaving you with 360 times 5 over 3. Okay? That is only to show you how it was done. Okay? And here's a table how we achieve this criteria. Okay? Sorry about that. And here's a table how we achieve this. Okay? A, 3 times A, sine of 3 times A, okay? And that's your values there. Okay? Now for the table you have the values of A, then you multiply the value of A by 3. This is where 3 times A comes into play. You then find the sign of 3 times A and the values are given in the table. Okay? And this is what you can plot your waveform, and this is what your waveform will come out like. Okay, let me just go in a little bit, make sure I can get it all in. Okay, now the head here should be a bit more curved, but okay, so but make sure yours is a bit more curvier, top and bottom. Okay, but it should actually fall into place. I got to let me see if I can get a text in today. That is. Okay. Now, lagging and leading angles. Okay. Now, lagging and leading angles. Now, lagging and leading angles. Now, a sine or cosine curve may not always start at 0. To show this, a periodic function is represented by y equals sine a plus or minus delta, or y equals cos a plus or minus delta. Well, it looks like delta to me, but it could also be a, little a, okay? That's the problem when you expand some of these, the lettering tends to change, okay? But never mind. We'll take it as a or delta. Where a, little a, is a phase displacement compared with y equals sine a or y equals cos a, okay? By drawing up a table of values, a graph of y equals sine a minus 60 degrees may be plotted as shown in figure 23.21. If y sine a is assumed to start at 0, then y equals sine a minus 60 starts 60 degrees later, i.e. has a 0 value 60 degrees later. Thus y equals sine a minus 60 degrees is said to be lagging y equals sine a by 60 degrees. Okay? And notice the emphasis there on lagging. Okay? And here we have lagging, and that's the point of lagging here. Okay? Once it goes minus, it means it's minus. It is a lagging factor. Okay, let me just look up, make sure that we get this all in. Okay. Okay. Now, by drawing up a table of values, a graph of y cos, okay, may be plotted, etc. And this is shown in figure 23.22. Okay, and I'm just going to go down to this. So make sure you take this in. Now try and do these examples for yourselves as well. Make sure you can understand them. Okay, that they're relevant. Well, they are relevant basically, but just make sure you understand the concept behind it. Okay, and I want to make sure you can read this. Okay. Okay, good. And here's your waveform. Okay, and let me pan back so we can get it in for full view. Okay, you can see that That's your ordinary waveform. This waveform here is lagging this waveform. Okay. It's figure 23.21. Okay. Let me just make sure I can go back and make it into full view. And you can see here that the amplitude is 1. Okay. Okay. Now a cosine curve is the same shape as a sine curve, but starts 90 degrees earlier, i.e. leads by 90 degrees. Hence cos A equals sine A plus 90 degrees. Okay. Now problem 8, sketch y equals sine 5 sine A. Well, let me be precise. Y equals 5 sine, open brackets, A plus 30 degrees, close brackets. But I normally tend to ignore that because as I'm writing it, I don't need to think that. But it's important that you bear that in mind and you take it as it is written. Okay? In your case. And here's the waveform for it. Well, this is not mainly to do with waveforms, and this is no practice for you to do. So basically, I will leave it at that now for you. You don't need my mouth over it all the time. Okay. So, and here we are. Okay. Now it is important to remember that pi is equal to 180 degrees. Where pi is divided by 3, the angle becomes 60 degrees. When using your calculator, determine whether you are working in radians or degrees. Okay, that is important. And problem 10, sketch y equals 2 cos omega t minus 3 pi over 10 over 1 cycle. Now we know the amplitude here is 2. Now I'm not going to spend a lot of time talking to you through this because this will now become familiar to yourselves. Once you've done the work at the top, you should now be able to apply the work in here. And you now know what pi is in regards to degrees. Okay? Okay, and here we are, 3 pi over 10 omega rads. Okay, let me just go back a little bit and let me just go in so we can clean it up in full. Okay. Okay. Now here I'm giving you some examples to do for yourselves, okay? And these are examples for you to follow through, okay? Once you've done a lot of this, it becomes automatic. You can see it and you can just do it in your head. And here I've given you the answers to the questions and the exercises, okay? In figure 23.26, let OR represent a vector that is free to rotate anticlockwise about 0 at a velocity of omega rads per second. A rotating vector is called a phasor. After a time in seconds, OR will have turned through an angle omega t radians, shown as angle tau in figure 23.26. Now, if ST is constructed perpendicular to OR, then sine omega t equals ST over OT, i.e. ST equals OT, sine omega t. Okay? Now, this is in reference to the sinusoidal waveform in regards to A sine omega t plus or minus, well, I will say delta or A. And here's what we're looking at, okay? It's telling you here that we can plot, using this here, we can plot these angles here, we can plot our waveform by using these exact angles here. And then these angles comes to a point somewhere here, across here. We can then plot it again further along here. And we can actually plot out our waveform using this omega rads in seconds, okay? Now make sure you read additional information, look up additional information for support to make sure you understand the concepts behind this, okay? If all such vertical components are projected onto a graph of y against omega t, a sine wave results of amplitude OR are shown in section 23.3. If phasor OR makes one revolution, i.e. omega 2 pi radians in t seconds, then the angular velocity omega equals 2 pi over t rads per second. Goodness me, I twisted that there for a second. Sorry about that. Now here t is known as the periodic time, okay? The number of complete cycles occurring per second is called the frequency. Frequency equals number of cycles over seconds, okay? So F equals 1 over t equals omega over 2 pi rads in hertz. i.e. F equals omega over 2 pi hertz. Hence, angular velocity equals omega equals 2 pi f rads per second. Now, the angular velocity is which you will be rotating. If it's a generation that you generated, then you will be cutting velocity at a given angle at so many cycles per second. And we use 50 cycles per second in the UK. Okay. Now, amplitude is a name given to the maximum or peak value of a sine wave, as explained in section 23.4. The amplitude of a sine wave shown in figure 23.26 has an amplitude of 1. A sine or cosine wave may not always start at 0. To show this, a periodic function is represented by y equals sine omega t plus or minus delta, etc. where delta is a phase displacement. Okay. Oh, sorry about that. Goodness me. Just go back a little bit. Just at the wrong angle in. Okay. Now, please note the angle omega t is measured in radians, and that carries on down to here, okay? i.e. rads omega over seconds. Equal omega t radians. Hence, delta should also be in radians. The relationship between degrees and radians is 360. Now, let's make sure we get this for you upright the right way. And large enough for you to see, so we don't need to be in doubt. Right, let's see, make sure, can we get that in? Yep. Okay, 360 equals 2 pi radians, or 180 degrees equals 1 pi radians. Hence, 1 rad equals 180 divided by 3. It's okay, I'm just trying to make sure that that I see what they're saying here. Oh goodness me, I'm still twisting it again. Let me work this out over. Let's check something. Make sure. Now I'm leaving it safe for a moment to right. Sorry, I'm back. I'm just looking at something, making sure that I'm there. Now, if we take hence 1 rad equals 180 divided by pi, and here we have pi is 3.141 or 3.142, which will give us 57.30. And for example, 71 degrees equals 71 times pi over 180 equals 1.239 rads. So you can convert degrees from degrees to radians simply by carrying out your multiplication and division factor, remembering of course that pi is 3.142. Okay, so okay, I had to make sure that what I was referring to and seeing was the correct information, so I had to make sure I check it for myself, even though I've checked it many times. But every time you come across these things, you forget what you did. Okay, so sorry about that. Well, it's my old age now anyway, so I'm allowed to take a bit longer. Okay, right, so there you can see how to convert radians to degrees and degrees to radians. Okay, and this is information you will need. Now look at the electrical principles section in my playlist, okay, as well, because you have additional information in there which can support your knowledge. Okay, the above gives you information in respect of converting degrees to radians and radians to degrees, where 1 rad equals 180 over pi equals 57 degrees. In this case, remember that pi is equal to 3.142 in its simplified form. To convert degrees to radians, for example 71 degrees, we do this process. And again here I've given you how that was done. Okay, now you don't need me to do this for any further or do a lot more talking. Okay, so I'm going to just bring the information up for you now to be working through for yourselves. Okay, here problem 11, try doing that for yourselves, and again I've shown you how that calculation has been done. Okay, and again here similar thing. Okay, again make sure you understand the concept behind this. Okay, it is for your information. Knowledge is power, use it. Okay, and again here I'll go through this slowly so you can see it. Okay, here I've simply shown you the calculation process which has been employed. Now you need to write this out for yourself. Do not try to do it off the screen. Okay, and again here are some other problems for you to resolve. Have a go at. Okay, and here I'm just simply telling you here now. Let me just bring this in for you so you can see what this is saying here. Okay, this is simply telling you, sorry, let's go over the side. That's simply telling you here that find the sine of minus 31 degrees, which is 0.5150. Okay, that's all I'm trying to indicate to you here. Okay, okay, let's make sure that we can bring this all into play. Okay, sorry about that, 1 second. Now these are just for you to do as calculations and examples worked for yourself. Okay, the fact that they've been already done is to enable you to understand the concept behind it. So do not give me the excuse that, oh well, it's already been done. Yeah, I know it's already been done. It's already been done, so you understand how to do it. Okay, and again that's our waveform. Let's step back a bit. Okay, let me just go back a little bit, make sure that we have everything in view. Okay, thank you. Good. Good. Okay, that will be it. Thank you for your time. Have a good day. I hope you will find this useful. Okay, again remember, study, study, study. Work, work, work is in your interest. No one else's. Have a good day. Bye-bye.